Okay, so I think we ended the last time right in the middle of an example, and we just had the last part to do. So all the way over to here. Okay. Quiz 5 has been posted. And just to give you a heads up, quiz 6, I'm going to post that pretty soon. Like later today, I think we'll probably get into Smith charts. And the next quiz is on Smith charts. So for those of you who want to get a jump on it, we won't get anywhere near all done today. We might not even get done on next Monday, but probably over the weekend or at the latest on Monday, quiz 6 will be posted, which is the second last one. So make sure you're staying on top of them because like I said, they can build up. And if you really want a good score, probably not going to happen the first time. Maybe you're awesome at them and you crush it the first time, but more often I hear people like, I did this one 10 times and I'm still only getting an 8 out of 10 or something like that, right? Because it's so easy to make a little calculator mistake or that sort of thing. So, you know, plan for that. Don't go with the mindset that my quiz score is terrible now, but I'm going to get it high later. No, no, no. Get them in the bag and go from there. So go through example 2.7. As I said last time, we're given a voltage generator here. The G, it's only a function of T because this is like the source on the bench. It's not a function of position because this is not a voltage on the transmission line. This is a voltage source that's coming from one point, one circuit or something, which will then go on a transmission line. And then we could figure out the voltage at any point on the line. But this is just kind of at the far left, at the beginning, the voltage source. 5 is the amplitude. That's you going into the lab to your signal generator and setting the amplitude to 5 volts. This, which we kind of, I let you think about the last time, I think, when it came up about what the frequency is, I think we wanted to calculate beta for the input impedance. And we said, well, what's beta? There's different formulas for beta. One of them is 2 pi over lambda. Then you could say, all right, well, what's lambda? A formula for lambda that you might remember is UP over F, but then we need F, right? So when you see anything in that form, it's always omega T. So this is always omega T. And just always remember that omega equals 2 pi F. And so you just solve that for F. So we said omega is 2 pi times 10 to the 9. So if we wanted to solve for F, it'd be omega divided by 2 pi. That's nice, isn't it? The 2 pi's cancel out. We're just left with 10 to the 9. 10 to the 9 is 1 gigahertz. So that's the frequency. It's in volts. We're given the internal impedance. We said it's a 50 ohm lossless airspace transmission line. 50 ohms, that says Z naught is 50 ohms. The characteristic impedance is 50 ohms. Lossless, that tells you you can use all those simplified equations that we derive for the lossless case where R prime equals 0 and G prime equals 0. Air-spaced, that tells you what? Yeah, UPSC, or the velocity of propagation, is the speed of light. So each one of those things, it's like chock full of information, right? So when you're doing one of these on like an exam or something, you're like, like you could like underline and go, I know what that means. That's like a whole set of maybe a subsection on your formula sheet. You're like, all right, I can use those sets of equations. Airspace, all right, C, UP equals C. We're given the line length, it's 5 centimeters, terminated in this load. Reflection coefficient, so we went through this the last time. The equation that you pretty much always use for the reflection coefficient is gamma equals ZL minus Z naught over ZL plus Z naught. Okay. So we did that. First, we're in rectangular form, which is the real and imaginary like that. And so we did that for the numerator and the denominator, but then we got to do the division, right? So then we flipped over to polar form so that we could easily do the division. The magnitude, the top magnitude divided by the bottom magnitude, the top angle minus the bottom angle. That gave us the reflection coefficient. Then we did the input impedance. So just remember what input impedance means. It means right where the transmission line is connected, which is at A prime, the input impedance is looking into that point. So it captures within the input impedance Z in, it takes into account all of the effects of the transmission line with the load ZL connected to it, so that we can replace it with this really simple circuit. And now you're in circuit land, okay? In other words, just like 240, because all of the effects of the transmission line are baked into Z in. So we used an equation. We didn't use these ones. We used a slightly different one, but the equations that I'll just refer to as the ones with the tan beta L in them, okay? Those are those kind of ugly Z in equations. And so we had everything in that. The only things in that formula are ZL, we're given it, Z naught, we're given it, and beta L. We're given L because L is the physical length of the transmission line in meters. And beta, we had to calculate it, 2 pi over lambda. And then we figured out what lambda was. There's other forms of that equation that would get you the same thing. So what did that get us to? I think we ended up with a Z in of, first we did it in polar form because we were doing that division thing again. So we wanted to get it in polar form. And I think we got something like 17.86 angle minus 45.4 degrees, which also equals about 12.5 minus J 12.7 ohms. So from the division, we got our answer in polar form, which is the 17.86 angle minus 45.4. From there, we could convert it to rectangular form to go get the 12.5 minus J 12.7. To get that, you would just do 17.86 times the sine, times the cos of minus 45.4 degrees. That would get you the real part, the 12.5. If you did 17.86 times the sine of minus 45.4 degrees, you would get the 12.7. Make sure you know what mode your calculator's in, because to calculate this, your calculator was probably just in radian mode, because for the tan beta L, that tan beta L is in radians. So your calculator has to be in radian mode to calculate that. But then if you convert it at some point into degrees, you got to make sure it's in degrees. So just be paranoid about what mode is my calculator in. So we have this, we have in both forms. And now we want to do the rest of the problem. C, the input voltage VI and input current II. So C. So that's B. And now we're on C. Okay, we want the input voltage VI. So we have that up here at the top left. And the first thing when you see something like that, you want to make sure you understand what it's asking for. So VI, you can see it's defined here as the input voltage across right where you connect the transmission line to the source. So we want to get the voltage right across there. And this is what we said the last time, where now that we've taken into account the transmission line effects in Z in, we can just treat this like a circuit problem. It's a voltage divider. So it's easier to think about it if you replace these with resistors, and maybe don't consider that as, you know, a phasor or something like that. Then it's just some voltage source and 2 series resistances, and you want to figure out what the voltage is across this resistance. Well, you would just do your normal voltage divider stuff. So you would do this one divided by the sum of these two multiplied by the voltage over here. That's how much of this voltage would be appearing across this load. And that's what we have up there at the top left. V of G, Z in over ZG plus ZN. So we can use that. We want to calculate VI, that's VI. Z in, we just calculated it, right? So I could have asked, or I could ask on an exam, just not even ask for Z in. I could just ask for what's VI. Then you come here and you go, oh, I have to calculate Z in. Now I got to go through, I got to calculate, you know, using the tan beta L formula. In order to do that, I need to know what beta is. In order to get beta, I maybe have to calculate lambda and so on and so on, right? We were given ZG in the question. So we have Zn, we have ZG. And we have VG kinda, okay? That's a phasor. But we're given it as a time domain. So now we first, in order to use that formula, the plain old voltage divider formula, we have to get VG tilde. Who wants to take a stab at what VG tilde, the phasor form of the generator voltage, is? So it's a bit of a weird one, right? Anybody? Kinda. Yeah, you could. Yep. Anybody? It's really easy. So all it is, what was that? Okay. So all it is, you're gonna like it, it's just 5. Okay. There's no phase angle. There's no like beta X or beta Z or any of that stuff, right? Because I said it's not a function of position, it's just a voltage source. There's no phase shift, there's no phi 0, there's no plus 15 degrees or anything like that. It's just 5 cos omega t. Now, do you remember what happens with the omega t when you go to the phasor domain? There's that e to the j omega t that you never write. It's there, it's this, but in the phasor domain, we don't write it. So all it is just 5. And if you like, you could go angle 0. You could say, is that right though? Do you remember how you go from the phasor domain back to the time domain? There's like a couple of steps you got to do. Step 1 is you multiply by e to the j omega t. So let's just say we did that. We'd have 5 e to the j omega t. And then we have to take the real part of it, right? And here's where our friend Euler comes in. Because if we were to convert that, well, we'd have the real part of what? We'd have like 5 cos omega t plus j5 sine omega t. Okay, that's just sine omega t. And of course, if we're doing the real part, then that's just 5 cos omega t, which is this thing. So it's deceivingly simple. It's just 5 because the cos omega t is captured in the e to the j omega t that we don't write in phasor form. So it's just 5. That's the tricky part to this problem. Other than that, it's simple, right? Any questions about why it's 5? Okay. So once we have that, then we can use the formula. Vi tilde equals Vg tilde Zin divided by Zg plus Zin. So what's this going to be? It is going to be 5 times Zin. Now, we have 2 forms of Zn. Both are fine. They're equivalent. But you can think ahead to where you're heading here. You're going to have to do a division. Division's easy in polar form. So we might as well write it down in polar form, which is the 17.86 angle minus 45.4. So that is our numerator. And in the denominator, well, again, we have our Z in both forms, but this time we're going to have to add ZG, which is given to us as 50. So we're going to have to, we'll do it in the rectangular form here. And so it'll be 50 plus 12.5 minus 12.7. So from here, it would be, 5 times 17.86. You could multiply that out if you wanted to, minus 45.4 degrees. And in the denominator, well, it'll be 62.5 minus, there should be a J in there, J, 12.7. And then you convert that to polar. So you convert that to polar and you'd get something like 63.78 angle minus 11.49, something like that. So this part here, the upper part, when you have a number like that, remember that number, when you just write a number, that really has an angle of 0 degrees, right? Because think about the way that we always do our coordinate system. The x-axis is the real, the y-axis is the imaginary. So if you have a 5, well, 5 is real number, so it's right on the real axis, which is an angle of 0. And so if you wrote that 5 as 5 angle 0 and then multiplied these two, well, you'd multiply the magnitudes and you'd add the phases. Just like how when we divide the magnitudes and we subtract the phases. This one has an angle of 0. So you'll multiply the magnitudes and you add the angles, but the angle's 0. So the easier way to look at that is just go, this is going to be 5 times 17.86 angle of whatever that angle is. So you'd get that number, 5 times 17.86. And then you would divide that by 63.87. You divide the magnitudes. And if you punch that in, I think you would get something like 1.4. Someone can check that if you'd like, but I think you get something like 1.4, but then we need our angle. And we can get our angle just kind of looking at this right here, because you can see minus 45.4 minus 11.5-ish, right? So if you did that, you do 45 minus 45.4 plus 11.49, be in the neighborhood of 34 degrees, minus 34 degrees, okay? This is a voltage, so don't forget that. It is our input voltage, so it has units of volts. So really the trickiest part of this one, I think, was the VG. Any questions about this one? Okay, last part. We also wanted the input current I tilde. I tilde, we're just in circuit land here. Like I'll come back here and, we can just use this if we want to. So think about this another way. If you wanted this voltage, well, if this current I is going through that, it's like, again, imagine it's a resistor. And the current going through the resistor, V equals IR, right? So here it's just V equals IZ. And we just figured out what V is. And last time we calculated what Z in is. And so we just do II equals VI divided by Z in. Okay, so equals VI tilde divided by Z in. Now we got both forms of Z in already, both polar form and rectangular form. And we have our VI here in polar form. We're going to do a division, so polar form is going to be easiest for us. So I will write this as our 1.4 angle minus 34 degrees divided by 17.86 angle minus 45.4 degrees. So to calculate this, you would do 1.4 divided by 17.86. That would be the magnitude. It'd be something, I think you'd get like 0.078, something in that ballpark. And to get the angle, you would do minus 34 minus 45.4. So it'd be plus. So it's like 11.4 or something like that. it's a current. So it has units of amps, or we could say it's about 78 angle 11.4 degrees milliamps. You could then convert this back to the time domain. It didn't ask us to do that here, but you could. What would it be if it said, calculate the current II in the time domain? So that's the amplitude. So that always goes in front, okay? Remember the e to the j omega t is always there. E to the j omega t really means cos omega t when you go to the time domain. So we have 78 milliamps. So it's 78 cos omega t, which is our cos 2 pi times 10 to the 9, plus 11.4 degrees. So that would be the thing. So it'd be like I at t equals like 78 cos 2 pi times 10 to the 9 plus 11.4 degrees, and that would be in milliamps. Be something like that. All right, and that's the end of this example. Any questions about this one? Any steps along the way? Any little things that are bugging you that you're not quite sure about or that seem a little fuzzy? Yeah. Definitely would be. Yep. Thank you for that. It's always cos omega t. Otherwise, it's just a number that you can punch into your calculator. Yeah, thanks. Any other questions? All right. So that's that one. We've already talked about the matched case, but we didn't really talk about it in terms of impedance. We talked about it in terms of the standing wave. So just a refresher, matched. When you hear that word, it's used all over the place, right? Then you think, well, what does that word mean? Matched means like two things are the same or two things are equal or they're right for each other, that sort of thing. And then you could just think about, well, what does that mean in terms of my transmission line? It means the characteristic impedance Z0 is equal to the load impedance ZL. That's what the matching is. And the reason why that's so important is because gamma is ZL minus Z0 over ZL plus Z0, meaning that if they're matched, if they're equal, the gamma equals 0. The reflection coefficient equals 0, means there's no reflection. If there's no reflected wave, there's nothing to interfere with the incident wave, which means kind of nothing happens. Like there's no standing wave. So now we just want to think, well, what does that mean in terms of the impedance on the line? That's what it means in terms of the standing wave ratio or how the standing waves are behaving, but what about the impedance? And it's a really simple thing. It means that it doesn't even matter where you look in. So you can look at the input of the line like AA prime. If you look towards the load for this match condition, it's just equal to Z0, which is equal to ZL. But the beautiful thing is, it doesn't matter where you look in. You could look in there, you could look in there, you could look there, any point along this line. If this is a 50 ohm line, which it is, and you connected up a 50 ohm resistor at the end of it, or the equivalent of a 50 ohm resistor, an antenna maybe that has a 50 ohm input impedance, then you've got a matched condition. If you looked at the impedance looking into here, you would just look like 50 ohms. Okay, it's kind of a weird thing to maybe think about, but you would just see 50 ohms. But if you went to the midpoint and looked towards the load, it would also be 50 ohms. This is one of the beautiful things about matching. Now your impedance isn't changing on the line. And it should make some sense because match means there's no reflected wave. If you remember, the only reason why our voltage magnitude was changing at different points in the transmission line was because the constructive and destructive interference was changing along the transmission line. If we get rid of that reflected wave, it's becomes much less interesting. Nothing's happening. It's just one wave going forward. And the impedance is the same everywhere. Okay. So that makes our life easy. Gamma equals 0. And the big thing here, and the reason why when you design circuits or systems or whatever at frequencies where transmission line concepts are important, one of the big reasons why you almost always want to match it is so that all the incident power gets delivered to the load. Back to the antenna example, if you've got a wave coming down and hitting this antenna, well, if you're transmitting antenna, you want to transmit that power. You want to deliver it. You want to transform it into electromagnetic radiation. All of the power that you're sending down the line, you would ideally like to be radiated. Anything that's reflected back is a waste. Okay, so you want to avoid that. And because of this, we are going to, maybe near the end of next week, maybe a week from today, we are going to get into matching networks so that even if ZL and Z0 aren't equal, we're going to try to make them equal. We're going to stick something in the middle that where the combination of the thing we stick in with the ZL makes it look like Z0. And then we don't have any reflections. Yep. Something like a capacitor inductor, so there's an imaginary part for ZL. We are definitely, that is definitely one method of matching and one that we are going to do. We are going to stick inductors and capacitors in there to be able to make it so that it looks like the impedance that we want. We are also going to stick in sections of transmission line to make it look the way that we want. I would say that's probably the part of maybe the entire course that students struggle with the most. But once it's like, it seems like chaos, it seems like black magic, it seems like, in fact, one of the Smith charts, the one that I think we're going to use, it's called black magic design at the top. And this field by many people is considered like black magic. You'll hear that a lot. And for these kind of matching networks, it's kind of like, it seems like black magic. It's like chaos. You don't know what to do, but then all of a sudden it kind of clicks. So you have to kind of fight through that. It's almost like a light switch gets turned on a lot. So, but we'll get there and we'll do lots of practice with them as well. And I hope to have the tutorials set up before then, so you can go and get more practice if you want as well. Okay. What if we shorted the line? So look top right. Here's where our ZL is. That's where our ZL normally goes, right? And if we just said ZL equals 0, that's a short circuit. And we know some stuff about this, right? What do we know? Well, we know ZL equals 0. That's kind of like a definition of a short circuit. We know gamma equals ZL minus Z0 over ZL plus Z0. So even if I hadn't written that there, you would just look at your basic gamma formula and you'd go 0 minus Z0 over 0 plus Z0. That's just minus Z0 over Z0. It equals -1. Okay. And then you could say, well, we have a formula for voltage on the transmission line. And that formula was like, what was it? It was V0 plus e to the j beta d plus gamma e to the minus j beta d. So for the case of a short circuit, we know that gamma equals -1. So we can plug -1 into there, which is what gives us this equation here. All right, so if we have this equation here, we can remember our basic Euler's formula. Okay, so if we have this in the brackets here, instead of x is just like means anything. It's not a position or anything like that. I'm just saying, like, in general, e to the j whatever equals cos whatever plus j whatever. I messed it up. E to the j whatever equals cos whatever plus j sine whatever. Okay. So if x was beta d, then it would be cos beta d plus j sine beta d. E to the minus j beta d would be cos beta d minus j sine beta d. And if you added them together, well, you subtracted them actually, you can just imagine those two, the top one minus the bottom one. The coses would go away, right? Because this one's equal to that one. So if you did e to the jx minus e to the minus jx, the coses go away. There'd be j sine x minus j sine x. So we'd have 2 j sine x v0 plus from there, okay? The current, if you remember, we've mostly been focusing on the voltage. The current, the only differences are, well, we've got this plus sign instead of minus, and we have to do the division by z naught. So you can look up there and go, well, what if it, instead of minus, it was plus? Well, you'd have cos x plus cos x. So you'd have 2 cos x. And you'd have j sine x minus j sine x, those would go away. So you would just have 2 cos x, and then you'd still have your v0 plus divided by z naught. All right. So, as we know, if we want impedance, we do voltage divided by current. That one divided by that one. 2j v0 plus sine beta d divided by 2v0 plus cos beta d over z naught. So we're going to get some stuff canceling, right? We're going to get the 2's canceling, the v0 plus canceling. We have a sine over cos. Sine x divided by cos x, that is tan, right? Sine divided by cos is tan. So we have tan beta d. We're left with our j and z naught. Now z naught's in the denominator of the denominator, so it goes up top. So we have this. So we're saying, just zooming out a little bit, sometimes it's easy to get so caught up in the little details of like this, you know, mathematical manipulation that you forget what you're doing. We have a transmission line. We've shorted it at the end. We are trying to calculate what the impedance looking into it is at any position D. So that's anywhere from like right where the short circuit is, anywhere along the line back to the input of the line. Now, before taking this class, if you went into your circuits lab and you just shorted something to ground and then looked at the impedance looking into it, well, the transmission line had no effect. So you saw whatever the thing was at the load, you saw a short circuit. If you hooked up your multimeter and tried to figure out what the resistance was, it would just say 0 because you've connected a short circuit to it, but not here. Here, it's given by this, okay? So what does that mean? Well, it's imaginary. It's got a J in there, right? So it could act like an inductor or a capacitor. It's going to depend on the wavelength, right? Because that's built into the beta. It's going to depend on the wavelength. But it's also going to depend on D, meaning that the impedance is changing at different points on the line, which should make sense. You might expect, I would say, if you thought about this beforehand, you might have come to 2 conclusions. Conclusion 1 would be, no, that doesn't make sense. Like if I short circuit here and I look into it, it's shorted. Like it's a piece of metal that is shorted to ground. It's going to look like a short circuit. You could have kind of rationalized that. Or you might have thought, wait a second here. If I short this, everything's getting reflected, right? My gamma is -1. my wave going back in the other direction, my V0 minus, has the same amplitude as the wave going this way, which means there's going to be a lot of interference, right? There's going to be places where they both add constructively up to double the voltage, places where they're perfectly out of phase and it goes to zero, meaning the voltage and current are varying wildly along this line, which means the impedance varies wildly along this line. In fact, it could be anything between zero, like a short circuit, or infinity, like an open circuit. So it's J Z naught. So J just means it's imaginary. It's a reactance. Z naught's whatever the characteristic impedance of the line is. And then we have beta D. So we're going to take this in a couple of cases here. We can say, well, we've got this, but tan can be positive or it can be negative. In other words, depending on the value of the beta D, the only difference between this one here and that one there is that is if you had a length of line L. So you can forget even about that small little distinction. It's really, that's just your distance from the load. Okay, D, because it can be a little confusing because for distance from the load, we've now used Z sometimes, we've used D sometimes, and sometimes we use L. And what I'm saying is they're all kind of the same thing, right? There's slight distinctions. Z and D are just the same, there's just a negative sign. L is just us saying the entire line is L long. So it's like D equals L to get back to the input. But all of it is really just starting at the load, how far away am I going down the line? Okay, so any impedance has a real part and an imaginary part. But from this, it only has an imaginary part. Kind of like inductors and capacitors only have imaginary parts. So the impedance of an inductor, what is it? J omega L. Kind of like J times something, right? This is J times something. So what we can say here is that if this tan beta L, as I said, that can be positive or negative, but if you just treat it as positive for the time being, kind of looks like an inductor. So what would the inductance be? Well, what we can do is just say, well, we know the impedance of an inductor. We'll say LEQ because it's kind of like we're going to figure out what the equivalent inductance is. We'd say, well, if we said J omega LEQ equals J Z naught tan beta L, this is for tan beta L greater than equal to 0. Basically, what we could say is we can make a section of shorted transmission line look just like an inductor. Because this is our impedance of an inductor. This is our impedance of our shorted transmission line. You can see they both have a J in there. So let's just kind of cross those out because there's a J on both sides. And let's just divide by the omega. Henry's. All right, so we have some transmission line. Let's say we know the Z naught, the characteristic impedance. Let's say we know what frequency we're working at. So omega is 2 pi f. So we know the Z naught, we know the omega. Beta is 2 pi over lambda. Lambda, you know, we could calculate that. It's UP over F. So as long as we know what the speed is and what the frequency is, we know beta. We can use a length of line L to get whatever value of inductance we want. It's kind of a weird thing, I think, because they're kind of two totally different things how you normally think about it, right? An inductor is normally like a coil of wire, right? And the magnetic field's all coupled together, and it has this behavior in circuits where it has this particular impedance that goes up with frequency. You put it in your circuit, you like buy an inductor and you solder it on your circuit board, right? And then something kind of seemingly totally unrelated, we have a section of transmission line and we've shorted it. But we can make those two things look exactly the same from a circuit perspective. Okay. Okay. That is only though if tan beta L is greater than 0. If it's less than 0, then what does that mean? Well, that means this whole thing is less than 0. Z naught's always positive, right? So you have J is just J, square root of -1, multiplied by something positive, Z naught's always positive. And we're saying if this thing is negative, then we have a negative reactance. We have minus J something. Minus J something, it's kind of like a capacitor, right? Impedance of a capacitor, what is it? 1 over J omega C. 1 over J omega C, whenever you flip the J, like if you take the J upstairs, it makes it negative. So 1 over J omega C, also the same as minus J over omega C. So now we have a minus J something, which looks like the case when this one is negative, which happens when tan beta L is negative. Okay, so we have 1 over J omega CEQ, some equivalent capacitance, equals J Z naught tan beta L, but this is for tan beta L less than or equal to 0. All right, and then we would want to solve for CEQ. How would we do that? Well, we take the CEQ over to the right side, and then we could bring down the whole thing on the right. It will all go in the denominator. What will we have? Well, we will have CEQ equals 1 divided by a bunch of stuff. What's the stuff? Well, the first thing we're going to have is J times J. So that's -1, because we're essentially multiplying this one on the right-hand side with J omega. J times J is going to be -1, so the whole thing's going to be minus. And then we just have the rest of it kind of multiplied out. So Z naught omega tan beta L. And then you might look at that and you might say, well, that's weird, because that is a negative capacitance then. Like it's a capacitance and it's got this negative sign in it. Ah, but this is only when tan beta L is negative, right? It's only for tan beta L negative, which means you have 2 minus signs, it becomes positive. So what I'm telling you is, if you're doing a circuit design at a frequency or wavelength where transmission line concepts are kind of in the ball game, like they're at play, and we know how to do that because we have our rule of thumb, right? We have a rule where we said we do the ratio of L to lambda, right? And if it's bigger than a certain number or less than a certain number, that tells us whether transmission line concepts need to be taken into account or not. So let's say you're doing a design. It's like back at the beginning of today, when we're talking about senior design projects, you wanted to go into industry, you wanted to work at Apple, designing some new, Apple goggles or whatever the augmented reality next thing's going to be. In it, it's got to have wireless connectivity, it's got to have Wi-Fi, it's got to have Bluetooth. Maybe it pairs to your phone or something like that. So maybe it's some new wireless communication thing where it's really low power, so it doesn't need a big battery in your goggles and pairs with your phone. that's going to be at the types of frequencies that we're talking about here. It's going to be, you know, a gigahertz, maybe up to tens of gigahertz. It's going to be in the realm where transmission line concepts are important. If you're dealing with the software behind it, or you're dealing with the digital circuits, you probably don't need to worry about this. But if your job is the one to deal with the antenna, or the connection from the antenna to, on the receiving side, let's say a filter, amplifier, all of these things before it gets converted to digital, where now it can go into the processor and you can do all your magic, right? With programming. But before that, there's kind of no getting around it, right? Like, we live in this analog world where we're sending electromagnetic waves back and forth. You got to have an antenna. When it receives it, it's a very high frequency analog signal, which then needs to be filtered and amplified and all this stuff. And all of those things need to be designed and connected together with transmission lines. Sometimes those circuits would need to have capacitors or inductors in them. So that's you 5 years from now. You're designing this circuit, and it's on a very small printed circuit board, let's say. And the circuit you're designing is at some number of gigahertz. You've thought back to your 370, you know transmission line concepts are important. You know you need to use, let's say, a capacitor. You got some options. You go to DigiKey or Mouser, right? That's a good option. You go to DigiKey or Mouser and you type in capacitor of whatever value you want. Okay, some number of picofarads or whatever. A pile of results are going to come up. It's going to be ridiculous. You're going to have to pour through this thing. If you've ever gone and searched for any components or anything like that, you'll know that there can be a lot of search results. Then you're going to have lots of different options. They're all the same capacitance value, okay? The same number of picofarads or whatever. You're going to get some leaded ones, meaning the type that you use in the labs. They got these big leads, these big wires off them that you can plug into breadboards. If you broke into your, you know, the iPad or your phone, you're not going to find a lot of those, right? You can think the whole circuit board isn't that much bigger than one of those big old leaded, you know, capacitors or something like that. Then you're going to find tons of surface mount components. Now you're starting to talk a little bit, right? So these are those little guys. If you've looked at any printed circuit boards, you see those little like square, like cube size, like kind of rectangular little guys that are soldered down on each side. And then not only, you're not just going to find one of those, you're going to find those in every size, from like decent size, you know, ones to like some that are so microscopically tiny you can barely see them. All right, so now you got lots of options there. And so then you'd start thinking, well, you know, you have to take into account how much do they cost? What's their physical size? Will it fit on the board? Is it going to get in the way of other things? So you have to think about all those things. But one thing that you definitely have to think about is you'd have to go through the data sheets and make sure those capacitors work at the frequency you're using them. When you guys do your circuits classes, you just kind of go, all right, I need a 1 picofarad capacitor, and you just get it and you stick it in the board and you just assume that that's 1 picofarad, right? If you pay no attention to it and you're at these high frequencies where all these concepts are important, not only might it not work as a 1 picofarad capacitor or whatever, it might actually behave as an inductor. So there's something called the self-resonant frequency. And when you go high enough in frequency, like the kind of stuff that we're dealing with here, there's a transition frequency where an inductor might look like a capacitor might look like an inductor. It may be a capacitor still looks like a capacitor, but it has a totally different value of capacitance. So we're going to do a lab for the 370 lab where we're going to look at kind of a few different types of capacitors. One, the leaded type like you'd use in the breadboards here. Another that's surface mount, and another that does this. So if you wanted to design a 1 picofarad capacitor, say, you've got a lot of options. You got the leaded option, you got surface mount. Within surface mount, you have a whole ton of different sizes. Or you could not use DigiKey or Mouser or any physical component that gets soldered on the board. But instead, you could just use a section of transmission line that's shorted at the end, or that's open circuited at the end. And so that's the next thing. This example would be good to kind of wrap your head around this a little bit more. We're going to do an example at probably the beginning of next class. But the last thing we'll do today is kind of the same thing, but with open circuits. And I'll come back to talk more about that, how you would use that open or that short circuited or open circuited line to implement a capacitor later, and what the advantages and disadvantages are. So if we do the same thing here, and we just say, well, if it's an open circuit, ZL equals infinity, and then our gamma, ZL minus Z naught over ZL plus Z naught, equals 1. Whereas before that was a minus, it's now a plus. So coming back here, looking at these, if we have a plus, well, then the cos is that, and the signs cancel. So from that, we get the 2 cos, whereas before we got the 2 J sine or whatever. And this time for this one, we have the minus. So it's sine. Other than that, they're pretty much the same. But now when we divide them, we don't get tan. We get cotangent. So cotangent of x is just 1 over tan x. That's all. But once again, we got j times something. We have a negative in there this time, but it's j times something. And since it's j times something, it is going to act like potentially an inductor or a capacitor. Okay, so we can use either short circuits or open circuited lines to create equivalent capacitors or inductors however we want. There's some pros and some cons to this that we're going to talk more about, I guess, next time, because we're almost out of time here. We've also got these relations that we probably won't use, but they are interesting. The Z in short circuit times Z in open circuit, if you take the square root, it equals Z naught. But we're probably not going to use those too much, so I wouldn't worry about them all that much. So with that, we are ready to go for next time. We're going to start with this example. All right. Okay, so that's it for today. That's it for this week. We will start next time with this example. And after this, we move right into Smith chart. So don't forget your rulers, your compasses, and bring some copies of the Smith chart for Monday, okay?